Mabel. Mabel.
Mabel.
Mabel. Mabel.
Mabel.
Mabel. Mabel.
Mabel.
It's doubling every year and extrapolated at 10 years from 1965 to 1975 from 60 components to 60,000 components on a chip.
First thing you have to tell him is,
Yeah.
guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over.
The future is parallel. Single cores are not getting any faster.
Well, it's a new week, and I don't know if you have a great week, but I think some of you might be thinking about as the same thing as the name of the song that we played before the class, Don't Call Me Up. So like this class, we use interactive teaching method. We ask you guys to discuss in breakout rooms, and well, but the main thing is that we want to let everybody like your thought might be other people's thoughts. So sometimes like if we can share those ideas together, it will help us a lot. It will help us understanding the idea a lot better. So that's why I would like to ask you guys to speak for yourself. Well, and sometimes you feel shy about speak for yourself. So like a lot of cases, like when I want to talk like some of my personal issues with my friend, I would technically say, hey, I have a friend and my friend has an issue, right? So that's why we want to put you in a breakout room, because right now, when you are expressing your thoughts or you are really like expressing your group thoughts, right? Instead of saying, this is my thought, it's saying about other people's thoughts. And hopefully that will make you feel better when we ask people to like speak up for the small group discussion. So please do try to like raise your hand so that it will make my life easier. Otherwise, we will still have to call somebody up to make the class keep going. So today we are going to continue our discussion on performance, but I know you guys hate this slide now because we have been seeing this slide a lot. But the main thing really want to put in want to tell you here is that don't forget, like every machine, no matter how good the machine, how bad the machine, no matter how big the machine, how small the machine, it's all von Neumann architecture, contains processor memory. And when we want to execute a program, we have to execute instructions by instruction. We have to go through those data access if necessary. And don't forget instructions, they are also in the memory. So this is the basic idea of von Neumann architecture. And well, to evaluate the performance of a von Neumann computer, what we learned last week is that the performance is essentially defined. Okay, first of all, defined. When I say defined, it means that that's the meaning, that's the definition, and it's not something that you can really change because that's the definitions. So the definition of the performance in computer architecture is technically 1 over the execution time. The longer the execution time, it means that the worse the performance because your performance number is smaller. So the shorter the execution time, meaning that your execution time is better. And we calculate execution time based on instruction count times CPI times cycle time. But if you know, this is because the nature of von Neumann architecture in a way that the length of a program depends on the how many instructions that your processor needs to execute when we are executing that program, and that's a dynamic instruction, right? And then depending on how much time you need to execute each instruction, which is in relation to your clock cycle time and how many clock cycles you need to execute an instruction. So Nick, you have a question.
Yeah. So you said performance is 1 over execution time. I just wanted to, since execution time is measured in seconds, would you say performance is like the inverse of that? Or
yeah, it's the inverse of your execution time. Exactly. That's the definition of the from the textbook.
So it would be 1 over seconds?
Yeah, but usually we just use that. We don't say the unit as 1 over seconds.
Okay.
Okay. Yeah. Okay. Cool. So yeah, that's a definition, and the definition how you calculate it is also coming from the nature that the von Neumann architecture must execute your program instruction by instruction, and so it's technically the result of how many dynamic instructions that you executed and what's the average time for each instructions to take. So that's the idea of von Neumann architecture and why it's important and why we evaluate the performance like that. And the thing is that another thing, right? Like people like to compare. People like to compare. If you, like me, grow up in somewhere in Asia, like your parents like to compare. Like every time your parents would say, "Hey, my child is better than yours," right? Well, people have different metrics, and I shouldn't talk too much about this. But the thing is that, okay, how to compare? How do we know who is better? So there should be a standard of that, right? Otherwise, everyone can bluffing like mine is better than yours, right? So here's the definition. And some people may say, well, this is not fair, but no, this is the definition, right? So y is n times faster than x is always execution time x over execution time y. So the speed up of y over x is always the execution time of x over execution time y, or you can say performance of y over performance of x, but I just don't want to confuse you. So the definition of speed up is just this, right? Y over x, speed up of y over x is the speed up of execution time x over execution time y. So that's the speed up. So using the execution time, using the speed up equation, you are able to say, hey, my machine is 1.25 times faster than yours. Okay, so this is basically what we have mentioned last week, the most high level bits you should know to continue in the class today. And so today we are going to keep talking about like what or who affects each factor in the performance equation. And we are going to talk about Amdahl's law and performance implications. So this is one of the questions that we ask you, and a lot of, and the answer from you guys is definitely changing after the breakout room discussion, right? So, and then I show you this demo in the very beginning of the class. A lot of you still don't trust it's real. So if you don't trust that, try to run it, right? But if you trust what you see from your screen, right? So adding a sort is basically making the instruction count more, which means that suppose adding more instructions should make your performance worse. But if the execution time is shorter, so what really makes the performance better is because by adding this sort, the CPI is better. So what magic behind this make the CPI is better? You will learn this in the next week, the lecture next week. Well, or if we are lucky, if we are fast enough, probably by the end of this week, right? But this is definitely something you will learn later, and that's why I have this demo throughout this class, right? But there are more examples like that. So let's see, like, okay, so here is another program, right? So from the algorithms teacher's perspective, right? this program makes no difference in their complexity, right? You should agree with that. It's all order n squared. So right now I'm giving you a demo, and some of you might already know the answer, right? But for some of you never experienced that, let me show this program. So this program is basically a matrix addition program, and I have some initialization code. And then here I perform the matrix addition. And if you are familiar with C programming language, when I compile it, if I put a -d A means that I'm defining A, it will take these pieces of code, which is exactly the version A. And if I didn't define A, then it's going to be the version B. So, and to verify the result, I randomly pick a number here. So, so right now, let me make two versions of this. So let me try to run this version A. So this is version A. So for the version A, it takes 1.2 seconds to finish. And let's right now run version B. So for version B, hey, the same complexity, but almost twice the amount of the time. So right now, I want you to tell me, like, how many of the following makes that happen? Well, yeah. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, it looks like quite a few of you select an answer, but there are also quite a few don't agree with that. So I think it's a good time for you guys to try to, like discuss with your friends. So let's go ahead. Wait, why it's not working? Oh boy. Let me do it again. So let me try to do that. Wait, why can I not? Well, okay. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so after discussion, now more of you think the answer is B. So can I have someone telling me like what your group is thinking about? Raise your hand, raise your hand. Don't be shy. It's your group, not you. Okay, I have Byron.
So what we said was that the instruction count is the same, so that doesn't change. And also the processor is the same. So the only thing that can really change is the CPI.
CPI, right? Okay, so awesome. So sometimes you might feel like, okay, how do I know this, right? So so look at this, right? The complexity of the program, both of them has the same program. Instruction count is roughly the same. It's the same processor, the clock rate, it should be the same, right? But now the question is like, what about the CPI? So so sometimes you think, well, how can I figure out what's the difference among the CPI and CF? And sometimes it's just slightly different in instruction counts, right? So how do I know this? Right, so in modern computer systems, especially modern processors, we all support performance counters, which keep accounting like what's happening in a system. So right now, I'm giving you a demo to show like how do you know what's going on there. So let's say like I can run this program and I can do like I can use perf, and I can do perf stat, which would give me the basic stat, and it will. When you run it, well, because you have to access the processor information, so it will require the root permission. But if you look at that, right? So this basically tells you that, well, you have, wow, this is million, billion. You have 14 billion instructions that has been executed, and it uses instructions per cycle, so it's basically the reverse of CPI. So it can execute like 1.54 instructions per cycle with the version B. But let's look at the version A. So if you look at the version A, it's a lot faster. And if you look at the instruction count, right, it's roughly the same, right? It's roughly the same. It's all about like 15 billions, 14 billions, right? However, look at the instruction per cycle. It's twice more, right? It's almost like, well, it's not twice more. It's about like 66% more, meaning that you have 1.5 times better CPI. So that's why your performance gets better. The instruction count is roughly the same. However, the CPI is a lot better with a different version, right? So so this also tells you what's going on here, right? So the reason is just because the CPI of one is better than another. Okay, so right now we all agree, like by adding more instructions, the programmer can, well, like adding a sort, the programmer can change the instruction count. But the instruction count doesn't mean, more instruction count doesn't mean the CPI is going to be worse or better, right? And by using different ways of iterating your loop, by using different ways of composing your program, you can change your CPI, right? So both examples, the previous two examples, I think we clearly showed that, right? But for this example, it's mainly because of the CPI, right? So right now, the third thing that we haven't answered is that, how about the cycle time? So here's the thing. Well, right now, those processors, like you previously see that our processor, we probably see that the processor can expose its own program counter, performance counters for us, right? So the processor right now, they have a lot of features for software programmer to use. So in fact, like Intel processors, they expose their capabilities to the system. If you're running a Linux, it's under /C/devices/system CPU. And there is also a subdirectory called CPU frequency, tells you the available frequencies. So let me go to the place that I have for this machine. So It's sys, devices, what else? Okay, CPU, right? So here's the directory. And as you can see, well, there are quite a few different subdirectory and what else? What is this? Okay, CPU. Well, system, oh, sorry, devices, system, CPU, and because this is a machine with 6 processors, so it's processor cores, so you can go to any of the processor and see what's going on there. And wow, you can see, whoa, there are quite a few stuff that you can poke and see what's going on there, and each processor is its own driver. But in short, if you want to see like, okay, what's the status of each processor, Linux has a /proc and CPU info. It tells you what kind of processor we are using and what's the current frequency of this processor. So as you can see here, right now the frequency of the processor is running at 800 megahertz. Is running at 800 megahertz. Okay, so it's interesting, right? Because you see like they expose their capabilities as in files. And in Unix, right, or say in Linux, like everything in file, your software programmer is supposed to be able to modify the content of the file. So the demo that right now I'm going to show you is that I wrote a script. The script, well, believe it or not, well, trust, well, no matter you want to take it or not, I hope you take it. Let's say like if you can do something with a script, you can definitely do something with using programming. You can definitely integrate part of the program into the script into your program, right? So the script is really simple. I just echo the frequency, the target frequency I want it to be, and then I modify one of the minimum frequency in a scaling. So let me run this script real quick, right? So first of all, because again, this is something that's protected. So usually you need root permission to do that. And let's run this script. So let me run source, change frequency, and well, the frequency is in, let me see. Okay, so if I do this, this is like 1.6 gigahertz. All right, so let's do it. Okay, so right now that's cat pros CPU info, right? You will see, hey, your CPU frequency is right now becoming 1.6 gigahertz, right? Well, and I can overclock it. Well, I can make the clock frequency higher, right? So right now is 3.2 gigahertz, right? But what if I try to do this, right? Okay. Woohoo, right? It goes up to 4 gigahertz, right? And what if I do it with 4.8? See? So here, it tells you that, it really tells you that, okay, when I set this frequency, some of you might think it's just a file, right? So maybe Linux is just reading a file and tell me the number, right? But when I try to put like 4.8 gigahertz, it's a frequency that this processor cannot accept. So it throws this error message for you. So through this demo, I hope you trust that, you believe that even the frequency, the cycle time, the programmer can affect. So in the system, programmer is the most powerful guy, right? You can do everything. You can change the instruction count, you can change the CPI, you can change the cycle time. All right. So right now, the second thing I want you to think, what programming languages can affect? What programming languages can affect? Okay, let's wrap up in 15 seconds. Okay, looks like everyone voted. So let me see. Okay, so most of you, well, 50%, slightly above 50% of you think it's C. So why don't we go ahead and discuss with your friend, and maybe that will change your mind. And sometimes maybe the two that you are thinking is different from others. Go. All right, if you are, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now the most popular answer is C. So meaning most of you think two of them would be affected by programming language. Can somebody share your thoughts with me? Like your groups, not yours. Okay, so I have tweet. Okay.
So our group said we pretty much agreed on that it's instruction count and NCPI because the compiler also affects that in terms of the programming language.
But, yeah, that's compiler, right? But how about the programming language itself?
We also agreed on instruction count and CPI. However, we're like iffy on clock rate, like Byron was iffy on the clock rate because of what you just demonstrated. We're not sure if that is also
well, but the thing is that, well, the programming language automatically do that.
No.
Right? If that's not something the programming language will do, then it's not something belongs to the category of programming language could affect, right? It's all the programmer try to do, right? So programming language itself doesn't have the feature, right? But the programmer will explicitly do it. So that's the programmer's feature, not the programming language's feature.
Okay, right? Got you. That's why we agreed on two. That's all.
Okay, so if you agree with that, right? So you know programming language has an effect on the performance. Right now, what I want to ask you is not your favorite programming language, but what programming language would be the most efficient in terms of the instruction count? Just pick one language that you think would give you the best instruction count? Oh, the worst instruction count, sorry. The worst instruction count. The highest instruction count. Okay, so let's wrap up in 15 seconds. Okay, it looks like everyone has voted. So let me share the result with you guys. So the result is very, very interesting. So it looks like, well, most of you think Python is the worst, and then Java is the second worst. C is the third worst, and C++ and Perl, they are the best in terms of the instruction count. Well, so why don't you go ahead, discuss with your friend, and you can have a vivid discussion on what's going on in programming languages. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, well, that's why we need the group discussion, right? A lot of you change your mind to, well, nobody pick A or B. Whew, right? And then like a lot of you think it's E, Python, and some of you think it's Java. So can some of the group share your mind with us? That will be a very interesting thing to look at. Like, okay, if not, then I will pick, let me see. Harris, you were previously raised your hand, right? So do you mind to tell us what your group is think?
Sure. So what we were thinking was that the language that would have the highest instruction count would be the highest level language, as there are more steps to essentially compile or decode each and every single instruction from that language. And so we thought it should be Python, as there would be more steps to break down that Python a line in Python code into, say, assembly code during runtime.
Okay, so first of all, then why not Java?
I don't know. I guess we figured it would be harder.
Another thing I want to correct you.
Okay.
High level, all the 5 languages that I listed here, they are categorized as high level languages in programming languages perspective or in computer architecture's perspective. So the high level and the low level language, the base is the assembly language. So assembly language is low level language, but everything that's beyond assembly language is considered as high level language. So C, Java, Perl, Python, C++, they are all born equal. They are all high level languages, okay?
Okay.
Right, but you guys think Python needs more work to do, right?
Yeah.
Other thoughts? Thank you. Other thoughts? Okay, if not, then well, this is Hello World, right? Everybody knows how to write Hello World. So why don't we just just write Hello World for every language and try to have this try to run this program real quick and see what's going on. So, well, I actually have this version ready, right? So if let's see, like hello.c. So this is hello world.c, right? And let me like compile it. Hello and hello, well, -03 hello.c, right? Okay, so, and we have a good friend, right? Perf. And let me run hello.c. Hello, right? Okay, so it tells me it takes about, wow, 500,000 K instructions to just execute Hello World, right? So sometimes you guys think about Hello World is so easy, but it's actually taking this many instructions to execute. So it's actually not a short program in some in the perspective, right? And let's look at the C++ implementation. So this is C++ implementation, and we have to use namespace. We have to use cout, right? So let's see. And for C++, we have to use G++. And let's compile it as hello CPP. And okay, right now let's run hello. Well, hello _CPP. C. This time, it also finishes really quick. However, if you compare the instruction count, for C, it's 500,000. And you were thinking about, well, C sucks, right? However, C++ is even worse. It's close to 3 million instructions. It's close to 3 million instructions. All right, and then how about, so right now, at least we know C is better than C++. And how about other languages? So, well, some of you love Java. So I have a Java program, hello that, well, and actually CSE141 loves Java, right? So we have a hello world .java, right? So this is the very classic hello world program from Java, right? And let's do Java C. Oh, okay, I think, but do I have the class file? Yeah, well, fortunately, I have the class file that I already, well, but this machine, does it have Java virtual machine? Well, this is a new machine, so that's why. Default JRE. Okay. Okay, I do have Java now. Okay, let's do Java, well, hello world, but can be found. Which Java C? Wait, I don't have Java C? Oh, I only have Java virtual machine. Okay, so then this way I'm just running a Java hello world, and hopefully you will trust me. It's exactly the same program. At least you see hello world on the screen, right? But right now let's try to use perf to characterize it. And okay, here we go. So let's do Java hello world. Okay, see how many instructions are there? So this is million. Okay, 184 million instructions. So remember, C is half million. C++ is 3 million and Java is 184. Okay, so let's see. How about Perl? So a lot of you don't even remember Perl, right? But Perl used to be like people saying this is the most beautiful language in the world. You can discuss that with your programming language teacher. But I don't know if well, I mean, I don't really understand the beauty of Perl, but since people say that, let's accept that. Well, if I understand, I won't be a computer scientist. I will probably be an artist, right? So, but let's try to run Perl and see. See, so for Perl, it's about 10 million instructions. Still a lot better than whatever million, 184 million instructions than Java, right? So Perl is better. Okay, another one, which is probably the most popular one, the Python, right? So let's look at Python, hello world, hello.py, right? So this is the Python, just one line of code, right? Let's see how much this one line of code would take. So let's run Python, and this is hello.py. Okay, so for Python, it's actually not that bad, 27 million. So it's more than Perl, but less than Java. So what does that mean? So, well, this is the number that I previously got on another machine. And well, so for Java, right, it's giving you the most instruction count. And the line of code, this is the line of code the programmer has to write, right? So for the line of code, well, it sounds like C or C++ is more complicated, and Python is the simplest one, but you know, there's no direct reason to relate correlation between the instruction count and the line of code. And in terms of the performance impact on instruction count, it looks like, well, for C programming language, because how the instruction count is so low, so it's so easy for people even a terrible C code can outperform Java a lot. Right, because if you really know like the difference in instruction count in this way, right? Thinking about like this instruction count difference, how big the CPI needs to be optimized to beat C code. Okay, so Harry's question.
So my question is, why is it the case that Java versus like Python and Perl, why is it that Java has such a high?
Okay, so that's what I'm going to tell you about, right? So this is C code, right? So you guys already learned. So remember, so actually some of you don't think the first lecture is important, but it's actually something we have talked about in the first lecture. So for when you run a C code, right, you have the program that's already in the memory, right? So all you need to do is to load those and make them into the memory, right? And run those instructions. And let me explain why C++ has more instruction than C, because the thing is about like C is a very plain language and it doesn't have something like object oriented. But in C++ language, because it's object oriented, so before you initialize the system, like the C out, you need an implicit object to be initialized to to receive that the IO request, right? And creating that that object itself is an implicit overhead that the programmer doesn't know, and that's the language feature, right? So that describes. So the difference between C and C++ basically is not because of the way how they generate their machine code. It's more about the overhead of object-oriented design. So sometimes people think about object-oriented design is good, but it's actually a disaster for performance in this way, right? And then let's look at the language, the other language that we talk about, right? That's Java. So for Java, its overhead is like this. First of all, I have the Java compiler generate the bytecode, right? And the bytecode is some kind of machine language. And when you run your program, it's executing the bytecode, but who is executing the bytecode? The Java virtual machine. So the Java virtual machine itself has to translate the Java bytecode into machine instructions. So you are receiving Java bytecode and it's already a machine language, and you have to run the virtual machine to execute them, to execute the translation of that machine language into your target architecture code. So it's a two-step operation, right? And how about Perl and Python? So for Perl and Python, it's actually better in some sense because you don't have to execute that Java bytecode. All you need to do is just interpreting what's going on there and emit the instruction code. So that's why Python and Perl, they are a lot better than Java in some sense. All right, so other questions? Okay, so if you agree, right? So you will figure out that, well, compiled language sometimes it's not, well, a language with compiler doesn't mean the language is better, right? The nature of how the language is executed actually matters, right? So choosing the right programming language is very, very important. And if you want to be a performance programmer, an infrastructure programmer, which a lot of cloud companies that requires, it's very important for you to learn efficient programming languages and how to write efficient code using this programming languages. So if you don't know if you are not familiar with C or C++, it's not a bad time to start learning it. And if Java is the only language that you know, well, I encourage you to at least learn Python. If you don't even know Java, I guess you have a problem, right? So here's the thing, right? So what programming language can affect the instruction count, the CPI, right? And we have gave you sufficient amount of demos telling you like how that's going to be different, right? Through this 5 programming language. So hopefully you will get that, right? So finally, how compiler affects performance. Let me know, what do you guys think? Well, let's wrap up in 15 seconds. 5. Okay, I got everyone's answer, and looks like, well, so this time we got 60% of you think the answer is C. So I would like to skip the discussion for this question because I think you guys are probably clear on what's going on, but I still want one of you to clarify how that affects performance. Can I have somebody raise your hand? Okay, if not, okay, so I have Twee. You are the heroine.
So as you already demonstrated for us, it shows that the compiler affect the instruction count because for object-oriented language,
well, that's the language, right? The same language, the same compiler.
Yeah.
It didn't tell you, well, it's different language, different compilers, right? So it didn't tell you that much, right? Like in experiments, you can only change one thing, right? We change the programming language, we change the compiler. So that is not but we do have a demo before. What was that?
Are you still asking me?
Yeah.
The demo before, it's not Hello World.
Yeah, okay. So if you want to see how compiler affects, right? The demo that I would typically give is the, I would say, right? Compiler optimization, right? So let's compare, right? Previously we have the MADD code.
Is it the 03?
Yeah, so that's run MADD version A with 03 turn on, right? Like, okay, without it turn on is 1.2 seconds, with it turn on is about like 1 second, right? More than 20% speed up. Well, more than 120% performance gain, not speed up, right? Right, so that's a case like how compiler affects performance, right? But right now, okay, thank you. So, but right now, I do want to show you one thing. So previously, we have the MADD version A and MADD version B, right? And some of you think about like, okay, if I have a great compiler, do I really need to optimize my loop like that? So let's run it. So if you have the MADD version without or with compiler optimization, right? You will see the performance difference is very little, right? So if you wrote your code like the MADD version B, the compiler won't be able to help you that much, right? So the compiler can affect CPI, can affect IC, and that's what you will see previously in a demo. But one thing the compiler will not be able to do is that it can only optimize your code by reducing the instruction count, or maybe sometimes we have more instruction count, but the CPI is lower, right? But no matter what a compiler would be doing. Okay, Harris, do you have, okay, let me see, you have a question. Okay.
Actually, I was just going to ask, how does the compiler affect CPI? Because I can understand how it could modify like instruction count, but at the end of the day, does the compiler have any control over how long each?
Well, so the CPI, right? If you think about how CPI is calculated, is the breakdown of the instructions and the CPI per instructions, right? So by changing the composition of your instruction of a program, it changes the CPI.
Oh, the CPI is just the average then, like the
right,
average.
right.
But if
so
that's the case, then anytime you change instruction count, you are necessarily going to change CPI. Well,
that's true, right? But that's true. You are right. You are right. So basically, they are bind together.
All right. Thank you.
Okay. So, but the thing is that compiler optimization can only do this with very limited capabilities. So, like your code version A and B, right? It cannot help you because the most high level idea of compiler is that we want to make it as fast as possible, but under the guideline, not make it incorrect. So we have to make your program right. So if the programmer says that your loop has to run in this way, the compiler cannot change the order of the loop. So that's why for the measures addition version A and B, the compiler cannot do anything, because if the programmer says that you have to go through Y first, the compiler cannot. If you have to go through this first, the compiler cannot change. The compiler cannot change this, right? But the programmer can change this, because programmer is the only person who knows if this is going to be correct or not. It's going to give you the right result or not. Same thing here, right? Previously, we have the code saying that, well, adding a sort would help, right? But the compiler will not be able to add a sort, right? Because, well, I don't know if you really want to sort the data or not. So the truth is that a lot of people think about having a smart compiler. I don't have to be a good programmer to make our program efficient. The answer is no, because it cannot improve the crummy source code that you wrote, right? So, and previously, the computer architect has done a lot of things to improve the performance of the crummy software, and we will learn a lot of techniques later on. But right now, knowing that the compiler has its own limitation, it won't help you, right? Another thing, a lot of you have the misunderstanding about having like, okay, if I am a good programmer, right, I really need to ace in algorithm or data structures, right? So for those of you who didn't get a good grades in CSE 100 or 101, you are probably happy with what the following things that I'm going to talk about. What I really want to talk about is that a lot of algorithms, they are realistically not implementable or not feasible, and or say if you implement that algorithm is a disaster of performance. Because of what? Because the computational complexity. The complexity that you guys spend a lot of time calculating a lot of math, try to do a lot of proof or formation in your algorithm. It turns out that and when some of you try your best to lower the complexity, but turns out that it's in terms of performance, it doesn't really makes a lot of sense, because the world of algorithm, those theory people, they are assuming that we are living in a world that every line of pseudocode would take exactly the same amount of instructions to execute, and every instruction would take exactly the same amount of time, which is never possible, right? So they are teaching you programming in a world that never exists. So that's why computational complexity, they are very deviate from the, we really have a hard time of translating complexity to performance, right? Like I said, like previously we have the program order n log n, it performs better than order n. We have a program, a sorting program that that is order n log square n is better than n log n, right? So those are the examples that tells you, I shouldn't say the word useless, but how what can you guys give me a neutral word? Okay, how impractical or how, you know, fantastic in a way that is not really true, right? So that's a thing, right? And later on, even in the lecture today, we are going to, the next lecture, I'm going to give you another analysis, like in a future world of computing, maybe algorithm is not going to be that important, but that's set aside. So another thing that people are talking about is like instruction set architecture has its own, instruction set architecture also affect performance, right? Because thinking about for x86 instruction set architecture, because it's complex instruction set architecture, so you can reduce the instruction count. And for RISC-V MIPS, they are reduced instruction set of computers, it doesn't mean they reduce the instruction count. In fact, they reduce the number of available instructions and make your program longer, right? So they are having negative effects on instruction count. So when people are saying about like why right now in every data centers, right? So these days, if you pay attention to what's going on in the world of computation, is that Apple tried to abandon Intel and try to embrace ARM for the next generation of the laptop or say like personal computer products, and for but Intel doesn't seem to be really sad about it. And there are tons of reasons that I can tell you, but first of all, commercial-wise, right? If you are familiar with the history of Apple, it's actually a hardware company, and every hardware company take care of the margin of the product very well. So it's very hard to earn profit from making business with Apple. And in fact, it's more about like a fan than getting money from them. And the other thing is that for Intel, right, their biggest market segment is actually in data centers. So for data center computer, that's where we want high performance computing. And because x86 instruction set architecture has its own advantage of reduce the number of instructions required to implement a program. And so it already has the advantage of instruction count. And another thing is that some of you might think about, what about the CPI? So later on in next week, later in this week, we are going to talk about pipelining. And you will later on learn that with pipelining, then the instruction set architecture probably makes no difference in cycles per instruction anymore, because if everything is pipeline, on average, the cycles per instruction is roughly the same, and it's more about like how can you implement that pipeline more efficiently than the instruction set architecture from end. So the CPI itself, ARM is not going to give you a lot of benefits. And then it turns out that can ARM processor give you the highest clock rate? But right now, have you ever seen an ARM processor is running at a higher clock rate than x86? The answer is no. So it's very hard for an ARM processor, RISC-V processor, to beat the performance of x86. And plus, for Intel, they sell those data center processors by a grand or 2 grands or even more. And the margin is about like 90% per processor, then like 9% per processor for Apple, right? So I've been working Intel before, and I remember when they give the employee price for their microprocessor is actually, I think, 50% discount, meaning that how cheap the manufacturing cost of a processor is in Intel. So they are not too worried about losing the market of Apple, and actually it helps them to improve their the net margin. And on the other hand, as long as they can keep their ground in data center, they should be fine for another couple years. So that's what I thought about Intel, right? So, but what it really tells you is that instruction set architecture nowadays is mainly going to affect your instruction count. So this slide summarizes the important perspective about performance equation. So first of all, regarding instruction count, instruction set architecture, compiler, algorithm, programming language effects, right? So if you do have a way to make your instruction per statement per pseudocode is really is going to be the same, then the algorithm actually affects, right? Machine implementation, microarchitecture, compiler, application, algorithm, as I said, anything that would change the instruction count potentially would change the CPI, right? So programmer would affect that too. Programming language will affect that too. But for cycle time, programmer can set it. Microarchitecture will affect and the process technology will affect the highest clock rate that you would achieve, right? And for the microarchitecture part, you guys will probably have more some experience in. It's going to have some experience in the lab later, right? But the key point here is that programmer is the only one who can affect all the three factors. So that's why CSE141 computer architecture is in CS, because you are the one who can control everything in the world of computing. So summary, performance is 1 over execution time. Execution time is instruction count times CPI times CT. Okay, so there aren't that many laws in computer architecture, but there is one important law that I really wanted to know. So this is called M-DOS law. So M-DOS law is like this. It says the speed up of enhancing part of the program is 1 over 1 minus f plus f over s. And f is the fraction of time in the original program that you are going to apply an optimization to. And s is the speed up you can achieve on f. So that's something that's confusing you, I believe, because you might think, okay, previously you told me the only definition in computer architecture about speed up is execution time of baseline over the execution time of enhanced system. How come you give me another definition called M-DOS law? So here is my explanation to you. So M-DOS law is actually a reformation of the speed up definition. So M-DOS law rescales the execution time of your baseline program into 1. And let's say if you can affect a fraction of time, like the fraction means like how many percentage you can affect in the baseline program. So you can partition your program into f and 1 minus f. And if you can speed up f by, so when you are running the revised version of your program, the 1 minus f, that part shouldn't be affected. However, if you can speed up the f part, the execution time of the f part will be f over s. So if you do that, execution time of the baseline is 1, and the execution time of enhanced is 1 minus f plus f over s. That's where M-DOS law comes from. But so it's exactly the same, right? But now you might want to ask me, like, why M-DOS law is so important. And well, so let's go through this example real quick. So let's say like so previously I have a similar program like this, and if I just do the same math, right? If you calculate the speed up like using execution time over baseline over enhanced, it's going to be just 1.25. But if you consider the program in this way, right? So this program is saying about, well, I'm going to improve the performance of low store instructions, and 20% of them. But when we say 20% of them, this 20% is actually the instruction count rather than execution time, right? So when we say M-DOS law, the F is the execution time, part of the execution time, right? So so we have to find out how much time in the original program spent in low store. So if you dig it down a little bit, you will figure out for this program, 60% is in the original program is in low store. And if your optimization can improve the low store by twice, then what we really get is like this, right? We can, oh, sorry. So this program is not improving low store, but instead it's improving the rest, right? So the rest is 40%. And by speed up the rest by twice, you got a 1.25 times speed up. So it's exactly the same as the original version. However, you might think about like, okay, well, I can calculate the speed up using the speed up equation. But there are cases that you don't have the complete picture about the execution time. You only know, well, so this part takes about like whatever percent. And the speed up I can do with this whatever is like that. So let's see let's try with an example. Not sure how many of you know this game, Final Fantasy, right? So let's practice Final Fantasy and see if you have an idea like how to apply the estimated speed up in Final Fantasy. Let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so I have seen two extremes of answers, meaning that you guys really need discussion. So why don't you guys go ahead and discuss? wrap up in 15 seconds. Oops. Okay, looks like everyone has voted. So after discussion, the most popular answer right now is C. So can I have some of you telling me, like, how do you guys derive the answer that you selected? Okay, so I have Jia Peng.
So I just use Amdahl's law. So F will
So
be.
how do you apply?
So F will be 95%.
Okay, so Amdahl's law is 1 over minus F plus F over S, right? Yeah. So you said F is
0.95.
Okay, 0.95. And how about S?
S is 100.
Is 100, right? So, right, see, so for this question, right, if you use Amdahl's law, it's very easy for you to figure out that it's about 17 times, right? So that's the application of Amdahl's law by knowing which part is by knowing the speed up and the execution time spent on each part, right? So Amdahl's law can also be applied to multiple optimization. So for example, if you can identify disjoint part of optimization that you want to apply in your program, then just expand your Amdahl's law like this. So it's probably not too difficult for you to understand what's going on. But the main idea is that just draw a chart like this. You will figure out there are parts that are optimized by 1, optimized by 2, and there are parts that are not affected. And what if those optimization 2 and 1 are disjoint, are not disjoint? Then you have to figure out which part will be affected by both of them, and what's the speed up by applying both of them. So you will have to expand your equation of Amdahl's law like that. So so we are going to have more practice on Amdahl's law in the next lecture. But before you leave the classroom, there are quite a few things I want to let you know. So first of all, for assignment on, originally it due before the lecture, but I also understand that our TVA's office hours is previously not aligned with the assignment due date. So we will move the deadline to tonight. So if you still have not finished it, and you still have something that you want to revise, go ahead and do it. We have one reading quiz due tomorrow regarding the upcoming lecture. And again, if you want to ask questions on Piazza, and if you want to turn in assignments, if you want to perform reading quizzes on Canvas, if you want to download the slides, it's going to be on our website, and demo code will be available through a link on the website. Usually I would update it probably within an hour after the lecture. So give me some time, right? Because I also need to drink some cup of water. And if you really like to see the lecture again, or you miss a lecture, YouTube is your best friend. Other than that, I will see you tomorrow. And there's no lecture for lab tonight.
Mabel.